call is now being recorded.
Yes, welcome all. So this is AIC sponsored Prerna Center for ACST student at Vidya Pratishthan's Kamal Nayan Institute of Engineering and Technology, Baramati. Today we are attending this GATE session for the subject Electrical and Electronic Measurement, and the topic we will cover is the RL measurements methods, and we'll solve some GATE questions. So let us start the session.
With the help of bridge circuitry. So you know the bridge circuit means what? It is a simple null method where we compare, which works on the principle of comparison. The comparison among the resistance, and among them we have belonging to the DC, that is DC bridge. So first one is Weston, second one is Kelvin, and then voltmeter, ammeter method. Okay, so this is again I'm repeating for you. This one is inductance, this one is capacitance, this one is frequency. So for inductance we are having Maxwell, Hayes bridge, Owen bridge. For capacitance we are having Shearing bridge, and for frequency we are having Wien bridge. So these are nothing but a bridging mechanism or bridging circuitry which is used to measure the value of unknown resistance. So this Weston bridge part we have covered. Also we have solved one example based on Weston bridge. Now we will deal with Kelvin bridge. Okay, so bridge is nothing but what? It's a something electrical circuit which consists of three known branches. Likewise in Weston we have come across three known branch. So one branch is R1, one branch is R2, one is R3, and one unknown resistance branch or unknown element branch. Okay, so aim is to what? To have a null deflection or to have no potential difference. That is means it should give null deflection. Okay, so at the end we have obtained one equation, that is R1 by R3 is equal to R2 by R4, or R1 into R4 is equal to R2 into R3. So this is the balance equation for Weston bridge. Okay, so where it is applicable, definitely it is used for filtering purpose, linear and non-linear application. So because of this, bridge as classified as DC bridge, like your Weston, Kelvin bridge, then your mega ohm bridge, and AC bridge will be inductance, capacitance, and frequency. Okay, so for measuring a small value of resistance of around 1 ohm, we can either use ohm meter or Weston bridge. But if there is a case where the resistance value is less than 1 ohm, okay, we have seen the classification. Okay, we have seen the classification. For low resistance it is less than 1 ohm, for medium 1 ohm to 100 kilo ohm, and for high resistance it is greater than 100. Correct. For low resistance we are using Weston bridge and mega ohm. But when there is accuracy or precision is more important, in that case what will the methodology? Okay, so in that case, it is difficult to find out the value of resistance less than 1 ohm. Okay, so we use a shunt value of unknown resistor with high current ammeter form, which is nothing but 4-terminal resistor. So what is 4-terminal resistance? How we can use it for measurement of low value resistor? That is elaborated by Kelvin bridge. Okay, so let us first understood what is the purpose of Kelvin bridge. So definitely I'll say purpose is nothing but to have accurate or accuracy in low value of resistance. If you want to measure low value of resistance that is less than 1 ohm, I'll say, sir, you are already telling that 1 ohm resistance, less than 1 ohm resistance belong to the low resistance category. Yes, it is, but I'm talking about 1 ohm means less than 1 ohm is 0.0007 7 like one. So such type of measurement we are using. We need a basic accuracy in that particular measurement. That's why we are using Kelvin bridge. Okay, Western bridge is also acceptable, but it is having some kind of limitation. It cannot give that much precise reading. So far, we are moving for Kelvin bridge. So Kelvin bridge, if you look into the picture, clearly you can see this is nothing but a Western bridge, but simply modification of Western bridge. So this is a simple modification. Okay, so here R1 is there, R2 is there, R3 is there, Rx is there, unknown resistance is there. Just they have added something extra. So what is that? That we'll wanna see in Kelvin bridge. Okay, so sometimes we call it as Kelvin bridge, sometimes we call it as Kelvin double bridge. So this is a simple modified version of Western bridge, which can measure the resistance in the range of 1 1 ohm to, I'll write it down here just once please. So you just need to check how accurate it is. From 0. Not 4 times, so we can say it is a 1 2 3 4 5 6 0.1 micro ohm. So such type of accuracy is important where we can use Kelvin bridge. Okay, so let us understand what we are going to do in Kelvin bridge. Okay, I'll just rub it. Yes, so that's what it is named as. It is another set of ratio arm. So yesterday we have seen what do you mean by ratio arm. Ratio arm means it is point. It is the point where we are forming arm of that particular branch, that is nothing but ratio arm. So those who are known value which forms a ratio arm, and the standard one is nothing but the amount of or the branch through which you are running that particular resistance. Okay, so basic operation of Kelvin bridge is to understood from the basic construction and operation of Western bridge. So this is nothing but just a modification, and we will see what that modification is for. Okay, so what we have done, we have modified the connection of galvanometer. First I will just erase all this. Yes. So we look for what we have done. We have connected the galvanometer. Yes, galvanometer is there. We have added one point, that is 2 point M. How we have modified? If you look into the previous one, yes, if you just compare this, okay, just compare this one. What is the modification? Two branches are there. Yes, here are the two branches. Then after the galvanometer, it was just a simply straight line. Okay, in Kelvin, we instead of this simply straight line, we have connected across M and across N. Okay, and that is nothing but Kelvin bridge modification. So if you go in construction wise, we have modified connection of galvanometer 2 point M and connection of galvanometer 2 point N. Correct. So what will happen? Because of this connection, value of Rx will change. How? Yes. So Rx is my what? Rx is my what? Unknown resistance that we are need to measure. Correct. Same in your R4. Here R4 is your unknown resistance. So for that we have derived equation. R4 is nothing but your Rx. Clear? Yes. So if my galvanometer is connecting at point M, correct? So Rx plus Ry. So this is my another resistor. So it will get added. So for value of Rx higher than the actual. My previous value was Rx. Now it will Rx plus Ry. If it is at N point, if it is at N point, my knob is at N point. So value of Rx will be different. So Rx plus Ry, this is high value, higher than actual, and Rx minus Ry, this is lower value. Okay, so this value will get added into R3, so it will becomes R3 plus R1. Okay, so all this modification we are doing for just accuracy in low value of resistance measurement. Okay, so now you have understood what is the basic difference between Whetstone and Kelvin bridge. So basic difference is nothing but we have added certain value of resistance, that is Ry, in connection to the galvanometer. Okay, so we have added 2 points, that is point M, N. So M, N, these are just nomenclature. It is get differ by circuit to circuit. So in some cases I will call it as point A and B. So don't confuse or don't just focus on the connection diagram. Don't concentrate on this nomenclature. Okay, the point is they have just denoted by M. Here they have just denoted by N. In your book, if you're referring in Google data, then this nomenclature will be different. Okay, so and again this is the written path. So on this methodology, we are going to study Kelvin bridge. So till now we have just understood what is Kelvin bridge. So Kelvin bridge is nothing but addition of modification of Whetstone bridge. Here we have added or we have connected our galvanometer. Instead of directly connected with the branch point, we have added certain 2 points, that is point M and point N. So what is the role of point M and N? Because of this, your unknown resistance, the value of variable resistance is get increased with Rx plus Ry. So that we are obtaining higher value, and it get decreased with lower value. Okay, so Rx minus Ry. Okay, I hope you have understood this. Let's move further. So this is the derivation, but actually you are not needed at a certain point of view. This is nothing but what you are looking for, a derivation. Last, this is the best modification of Kelvin double bridge. Okay, so if you just remember, this is nothing but Kelvin bridge. Now this is Kelvin double bridge. So why it is called a double bridge, that we will cover in this slide. Okay, and on that basis we are going to perform our second practical, that is measurement of low resistance using Kelvin double bridge experiment. Okay, so first slide it was just to explain what is Kelvin bridge, and now we are modify that construction of Kelvin bridge, and so that's why we call that Kelvin double bridge. Okay, so let us move for principle and working of this Kelvin double bridge, and then we'll move for our practical. Okay, so as we know, this is a modification of Whetstone bridge. Whetstone bridge is just to measure the value less than 1 ohm, but if we want to measure the resistance below 1 ohm, okay, Western has a limitation of less than 1 ohm. But what if the value is much less than 1 ohm? In that case, you need another device, that is nothing but your Kelvin bridge. Okay, so because of this, we are using certain leads for galvanometer, and because of this, they have added certain resistors. So in technical term, this M and N, the connecting wire, we are called it as lead. And if you are considering any copper wire or any conductor, it has certain resistance. So definitely the leads that we are connecting, it also having certain types of resistance, and that is nothing but your Ry. Clear? So that is the amount of resistance that is added to the Kelvin bridge. Okay, now so if you look into the Kelvin double bridge, first we'll read out what they have given. To overcome the problem of Kelvin bridge, the new bridge, okay, is introduced, which is used for precise measurement of low resistance, called as Kelvin double bridge. So this precise measurement is nothing but much less than 1 ohm. Okay, construction. For the construction, they are consist of 2 ratio arm. Yes, this is first arm, this is second arm. 2 ratio arm. Connected resistance are PQ, capital P, capital Q, then small p, small q, and S, that is nothing but yours this added resistance. Now this resistance is nothing but your connecting lead resistance. So which are connecting lead? This one. The point from galvanometer to the that M point and point from galvanometer to the end point, we are using certain conductor, and you know each conductor having certain kind of resistance. So that is nothing but that particular resistance. Okay. R is the resistance of slide wire. So here that is another wire which is connected across this, that is connecting wire. So that is nothing but this one. R is the slide wire. I'm going in detail one by one, just have focus on it. So R is the resistance of slide wire, and capital R. So here you can also capital R is the value of unknown resistance. So capital R is nothing but here this one. Okay. Galvanometer is connected between point F and H. So where it is point F and H. So this is F, and this one is H. Yes. Now working. Why they are saying by adjusting the balance condition, we can find the unknown resistance. So how we can adjust the balance resistance? We just form one equation, and on that basis we will vary particular value of P, capital Q, small p, and small q. And if galvanometer when it will give null deflection, then we will say our bridge is balanced, and it is measured whatever the value that is present at that particular instant, that is nothing but your Kelvin double bridge experiment, and we will obtain a precise reading of our experiment. Correct? Let me clear this first. Yeah. So this is what we are looking for. So construction wise, so the construction of Kelvin double bridge is similar to Western bridge, but only the difference is consisting of two arms. Okay. So what they are consisting of? Two arms. So that is one arm is P and Q, and another arm is small p and small q. Correct? Now the small p and q are being connected to the one end of galvanometer, suppose at this point H, and capital P and Q are connected at this point F. Correct? So this connection will minimize the effect of connecting lead, and we will get the value of unknown resistance. So what is the basic difference if you just compare between these? Okay, this one also clear. We come to know this. What is the basic difference here and here? See, R1, R2 are there. So that is here they are replaced by P and Q. Okay, so I am intentionally I have made these changes because some student might get confused. So they always think that the R1 and R2 is there, then it is Western and Kelvin. No, these are just nomenclature. You have to just look for this branch. Okay, if this branch is there, then you can say it is a Western bridge, and if this branch is added, then we are saying Kelvin bridge. Okay, this is the way to identify which bridge it is. Okay, so R1 and R2 are nothing but here P and Q. Clear? Then R3 and Rx are nothing but here this R and S. Correct? Then you will say, sir, why P and Q? So P and Q nothing but this is the resistance of this connecting wire from galvanometer to M, and the resistance of this connecting wire from galvanometer to N. So that resistance we have considered as, so here you can compare this one. Okay, these are connecting wire, which is nothing but this is from galvanometer to M point, from galvanometer to N point. These are nothing but this. But being precise, we have considered here their resistance. Okay, now you have understood what is Kelvin double bridge. Now they are forming two parallel ratio arm. That's why it is called as double bridge. And who have proposed this? Kelvin. So it is called as Kelvin double bridge. Okay, that's it about Kelvin double bridge. Okay, here there is no any mathematical model or what we can say derivation is there, but there is no need at this point of concern. I have just added it for you. So this is what Kelvin bridge is, consisting of two parallel branches, two ratio arms, and consisting of resistance of leading that not leading that particular lead, connecting lead. Okay, so that is nothing but this one. Okay, so what is the benefit or the features of this Kelvin double bridge? So features is it can measure the resistance value, can measure a resistance value. Here is see the features. Okay. Yeah. Yes, now it is. So features of Kelvin double bridge is what I'll say KD, Kelvin double bridge. Okay, features. Yes. So what you understood from Kelvin double bridge? Why we are moving for Kelvin instead of Weston? Is anyone? Please help me. Because of
Major small resistance.
very, very measure a small value of resistance. Now being precise, Weston is also measuring used for measuring small value of resistance, but it has some limitation up to 1 or less than 1 ohm. But being Kelvin double bridge, we can measure the resistance much smaller value, that is from 1 micro ampere. Okay. The second one is, so we have less power consumption. This is the second one, less power consumption. Sensitivity is high sensitivity. Yes, because we are measuring such low value of resistance, so it means it have high sensitivity. Okay, then what are the, if there are features, so there of course there should be some limitation or drawback. So what are the limitation? If you are using such equipment for high sensitivity, so your galvanometer should be that much sensitive. The galvanometer we are using in Weston Beach, same galvanometer we cannot use here. Yes, of course it is, because same galvanometer we are using here, then it will not give a precise reading. Okay, so we should use sensitive galvanometer. That is nothing but it is a limitation of Kelvin double bridge. To obtain high sensitivity, when we are talking about the sensitivity, current ratio is always there. Okay, so current and sensitivity are the correlate to each other. Okay, so we will require high amount of current also. Current should be high so that we will use it for measurement of resistance. What we are doing, we are actually passing the current, through this resistance. What is Ohm's law? A current opposition to the flow of current. So definitely we will need high amount of current to have a good accuracy in resistance. Correct? Okay, it's gone. Okay. So these are the some features and demerits of Kelvin double bridge. Okay. So basically it is used to measure the unknown value of resistance. Okay. So this is all about Kelvin double bridge experiment, theoretical part. Now we'll move to the experimental setup. Okay. Is there any doubt so far? Is there any doubt between Kelvin bridge and between Kelvin double bridge? So that we can move for the experiment.
Yes, sir.
Yes, please. Should we go ahead?
Yes, sir.
Okay, okay. So now we'll move for the experimental set. Okay. So to have better understanding, I have searched out one virtual setup. Okay. So what do you mean by virtual setup? Instead of performing, is it visible? Is my screen visible?
Yes, sir.
Yes. So please concentrate very carefully. I have find out something interesting for measurement of resistance by Kelvin double bridge. This is nothing but we are varying a virtual reading. Okay, now you better know what is your virtual and physical reading. Instead of going for the lab manual, going through just lab manual, this is the better one. We can go for it. Okay, so we'll follow certain procedure. Okay, this is given by virtual laboratory. They have proposed this experimental setup. Okay, the aim is what we are looking for. We are looking for second experiment, that is measurement of low resistance using Kelvin double bridge. Okay, this is what we are studying. Yes. First, let us start with the theory. The objective is what Kelvin double bridge may be used for precision measurement. Yes, we are using it for precision measurement of four terminal low resistance. So these are my four terminal 1, 2, 3, 4. Okay, four terminal resistance have two current leading terminals and two potential terminals across the resistance equals the marked nominal value. This is because current must enter and leave the resistor. Obviously, current should leave, enter from this, and it should leave from this circuit, so that we can give the galvanometer reading. Okay, this is the object. This is nothing but your circuit diagram. Okay, this is what we are look here. Here it is. Yes, we are look here. Correct? It is same. Okay, yeah. So based on that, we are having some experimental setup. Okay, so what we'll do, we will first read out the procedure and then we will look for this. Yeah. Yes. So what? Yes. Can anyone read out the first step procedure? First point. What is first point? Not I will do it for you. Yes, I can do that. Yes, Parth. Parth.
Yes, sir.
Yes. Read out first point.
Set the voltage V is equal to 12 volt and switch on the bulb. Keep switch yes in short mode and adjust the rheostat RS to maintain the current 2 ampere, 3 ampere, 4 ampere or 5 ampere in the circuit.
Yes. So what you understood? What they are saying? We will go one by one. Huh? We will read out the first one and then we will do some modification in this experiment. Okay. I will just zoom out so we'll have both on the same screen. Yeah. What they have said? What they have said? First, set the voltage to 12 volts. Okay. So this is my experimental setup. Okay. You can find out your all experiment, all your element. Okay. So this is nothing but your RA, RB, RA, and RB. See, here the nomenclature has been changed. So what we have seen? Yes, P and Q. These are nothing but here RA and RB. Small p and small q, here nothing but RA small, RB small. Okay, then we are having unknown resistance and your connecting resistance, that is this is S and this is X. Here we are having voltage and this current. So this is nothing but voltage 12 volt and this is nothing but current meter. Okay, among this, sorry, among this we are having variable resistance and ammeter, that is nothing but this one, variable resistance and ammeter. Okay, so if you map what we have done, we have just done mapping of our theoretical with the practical one. Okay, now let us start with the procedure. First is what? Set the voltage to 12 volt. So which is my voltage source? This one. So I will just change it. So I will keep it as 12 volt. Okay, दिसते का तुम्हाला हे? Should I zoom in? Yes. Now this is 12 volt. ठीक है, आता तुम्हाला दिसेल. Now it is, we have keep it as 12 volt. What is the next step? And switch on the board. So to switch on the board, we are having this switch button. Okay, this one. Okay, now it is at 0, we will switch it on. So as soon as switch it on, we will observe some kind of changes. Sanga bar, which parameter are going to change? What kind of change you are observing? Yes, anyone? When I switch it on, I switch on the supply to my circuit. What is the change?
Galvanometer में reading.
Yes, pardon.
Current increasing.
Yes, yes. So as soon as switch it on or switch it off, so these meter readings are at 0 position. You can observe it here. Is it at 0 position? As soon as switch on, it gets changes. Okay. Value of resistance are remain same, but change in measuring instrument. Okay. That is the change. Yes. Next is what? Keep switch S in short mode. So where switch S is nothing but this one. We will keep it in short mode. ठीक है? Adjust the rheostat to maintain the current 2 ampere, 3 ampere, 4 ampere or 5 ampere, whatever you require. Okay, so we have to adjust this resistance RS to have the resistance of high current. Okay, so as just we have seen the drawback of Kelvin double bridge, that we have to keep high value of high amount of resistance. Clear? So we will adjust it is, and accordingly our meter reading will change. Okay, so let us observe it. As soon as I reducing my value of resistance, the current parameter is gonna increase. Okay, so for one value of resistance, it is 12 ampere. Clear? So have you find out the relation? If I am reducing, I am varying the resistance, current is gonna change. Okay, so 0, 3, 6, -3, -6, these are nothing but my calibrated scale. Okay, so what they are saying, keep it as 2 ampere, 3 ampere, 4 ampere or 5 ampere. We will try to keep it at 5 ampere. Okay, so if I am increasing the resistance, my current is gonna reduce. So this follows your Ohm's law, opposition to the flow of current. Have you find out? Visualize here, if I am reducing the resistance, current is going to increase in the circuitry. Means 10 ampere amount of current is flowing through the circuitry initially. When I am starting increasing the resistance, the amount of current flowing through the circuit is going to reduce. Okay? This is what your Ohm's law says. Okay? We will keep it at 5 ampere. Now it is at 5 ampere. Okay? Yes. करेगा first step. Have you understood? Yes, Kishan, Aniket.
Yes, sir.
Yeah. So what do you find out? We have just apply our Ohm's law. This is my current, measuring current, and this is my resistance. If I am increasing the resistance, current gonna reduce. If I am increasing the current, resistance gonna increase. Okay. So then set the first step is, we have keeping voltage as 12 volt. We have keep voltage as 12 volt, and we are keeping the voltage just one second. Okay, so first step was, we will keep the voltage as 12 volt and we will vary. We will switch on the board, then we will vary the resistance, and according to the resistance, ammeter it is gonna change. That is the first step. Yes. Second one, Kishan, read out the second procedure.
Yes, sir.
Yes.
Then set switch to open mode and set low resistance value within 0.01 to 0.001 to 0.01 ohm. From set the unknown resistance, yes, from box.
Okay, thank you, Kishan. So what is the second step? They are saying then set switch S to open mode. Previously it was in what they are saying, keep switch in short circuit. Keep switch in short circuit. Now they are saying now you have adjusted your resistance and you have keep your ammeter at 5 ampere. Now switch your circuitry to open. Okay. Now we have open our circuitry. So as soon as I open, what is gonna change? The amount of resistance. Have you observed here? Now I am seeing open. Okay, so it going showing deflection. Zero deflection. Okay, zero deflection means what? Now we have switched to open mode. Okay, now set the low resistance value within, they are saying you have to keep the low resistance value within this range. So where is low resistance value knob? Where is low resistance value knob? Here it is. Okay, this one is here. So it is already here and we can keep this as from here also. Set the unknown resistance value. No, something is different. Just 1 second. Set the low resistance value within switch open mode. Okay, so this is open mode. We have set, yes, this is low resistance. Yes, it is. So they have did see. So there is change in just notation. So we have to find out notation. S is a notation. So here S is a notation. So we have to keep it. So I'll change by here. So you can observe now it is not actually showing here, but it is 0.004. Okay. Yes. Now move to the next one. Yes, we will read out the third procedure. In second procedure, just what we have done, we have just keep the switch S into the open position and we have set a value of unknown resistance. Okay. Now, so what value we are wearing? We are wearing the unknown resistance to have the null deflection. Clear? Yes. The third step. Who is going to read out? Aniket.
Yes, sir.
Yes.
Then set switch yes to bridge mode and switch K to open mode.
Yes. So you can just note down here when you are following certain procedure, you just need to concentrate on nomenclature, notation. So here S is a notation, that is set switch S. We have to keep into the bridge mode. So we will change that switch S into the bridge mode. So from where we have started from short one, then we have keep it open. Now we are going to bridge mode. Means yes. So as soon as switch it into bridge mode, there is a change. You can observe here. Okay, here you can observe. As soon as switch into the bridge mode, there is a change in the value. Okay, Alaga. So this is nothing but
Yes, sir.
yes. We have entered our circuitry into the bridge circuitry. Okay. Yes. Who is gonna read out next point? Point number 4. Yes, Divya.
Vary the value of RA, RB, RA and RB from this control box below or directly put the value in the box of respective elements to get zero deflection on the millivoltmeter pointer.
Okay. Okay. So what they are saying now, this is your task. Now my bridge circuit is in your scope. You have to vary the value of RA, RB. Let us find out where RA and RB. So this is my RA, this is my RB. Then small RA and small RB, small RA and small RB from your control box. Okay, or by the respective value, so that you can have zero deflection. Okay, so what we are achieving? We need to achieve here zero deflection. So we can vary from here. Okay, so we'll start with RA. ठीक आहे, त्यांनी असं सांगितलंय का just vary the value of RA, keep RB and remaining thing as it. No, they are saying vary the value of all the four so that you can achieve zero deflection. But in Westone, we are varying only the one resistance. Do you remember? In Westone, we are varying only the one register. Okay? We are varying only the R4. So this is the basic difference. And in this way, we are achieving a precise measurement. Okay? So let us vary this one. Okay? I'll choose it one. So we'll come to know. Yeah. So let us start varying. I'm switching it from 1.4, 1.7, 1.8. You can observe here. Now it is in negative reading. Yes. Now it is in positive state. Okay. Just check here. If we vary the RB, there is a sudden change from, if RB value is from 1.3 to 1.4, you can observe it is negative, and for 1.4 it is 0.00025. So we have achieved our basic zero deflection, but it is not accurate still. Yes, yeah, we have achieved it. Okay, what they are saying, we have to keep it as 0.001. Okay, and now it is 0.0025. So basically we have achieved our zero deflection. But for your understanding, I am gonna vary again so we can observe the change. Yes, so you can observe here the deflection of the pointer also. Okay, suppose I am here introducing 23. Yes, so my pointer is at this position, so it is not showing null deflection. येते का लक्षात? Means what? We have to vary all these four resistors so that we will having a null deflection. So what was it is? It is 1.4. Okay? Yes. So we'll again vary it for. See, the pointer is going. This is your null deflection. At the center, it is your null deflection. We will go for it. Yes. This is what we have achieved. Now it is in null deflection. Okay. Again, we're gonna change. Yes, now it is not in null deflection because it is showing. We are looking for 3 digit 0.001. Okay, 0.001. But it is, we have in previous stage we have achieved 0.001. See, 0.00, what change? Yes, 0.00025. So it is acceptable that you have achieved null deflection. And this is how we are using our Kelvin double bridge to measure the value of unknown resistance. Okay? So this is nothing but your experiment number 2, the measurement of low resistance using Kelvin double bridge. In next session, we will come across ammeter, voltmeter.
Okay, so I have dropped one link in your chat box. Kindly go through it, fill the feedback form, and we will resume the session very shortly.
Yes, Parth, is it visible?
Yes, sir.
So let us start with our first point from unit number 2, that is measurement of resistance. Okay, so before that, yes, please help me with the types of resistor. Yes, which are different types of resistor. Yes, types of resistor. Types of resistor. Okay, I'll start. One is fixed. Then fixed resistor. Then hello, am I audible?
Yes, sir.
Then what's going on? We are looking for measurement of resistance, and for that we should go through this passive element either for resistance, capacitance and inductance, and from that we are concentrating on first we are learning different measurement techniques for our resistance, and these are classified as first one is fixed, then speak out, variable, then linear, then सर तुमचा तुम्हीच बोला आम्ही फक्त ऐकतो नॉन लिनियर then after that low value, then we have medium, then we have high value resistor. Correct? Okay. So I will not wait for your response because of your it's just tremendous. Okay. So without wasting time, we'll start with our first point, that is measurement of resistance. Okay. So what we are look for? We are look for why there is a need of such resistance in our electrical appliances. So we have come across certain examples of cable manufacturers. We have certain examples of three-phase, single-phase supplies. Also, we have come across motor, generator. These are some equipment where resistance of that particular material has certain importance. Okay. So on the base of that, we will start with our first classification based on we'll start with our classification based on its type. So first we will have low resistance, then we have medium, then we have large resistance. Okay. So value of low resistance is what? It should be between, not between, it should be less than 1 ohm. For medium resistance, value of this resistance should be between 1 ohm to 100 kilo ohm, and if value of resistance is greater than 100 kilo ohm, then it will belongs to the high value of resistance. Okay, so these are some classification. These are some classification, but before that, we should know which are the methods for the measurement of this particular resistance. Okay, so basically, we know one formula, that is Ohm's law. What Ohm's law says? V is equal to what? E is equal to
IR.
IR. That is nothing but Ohm's law. Based on that, we will calculate value of resistance. This a basic fundamental law we all know. So based on this, resistance can be calculated by measuring current and voltage using Ohm's law. So that is nothing but Ohm's law. That's it. Correct? Yes. So as a result, a circuit resistance value can be determined if we know the value of current and voltage. This is the basic formula of Ohm's law. Now we have classified this in three terms. One is low resistance, then we have classified as medium resistance, and we have classified as high value of resistance. So based on that, there are certain different methods. There are certain methods of measurement based on low resistance, medium resistance, and high resistance. Okay, so in this topic, we will look over different methods which is used for measurement of low resistance, different methods which will be used for measurement of high and as well as medium resistance. Okay, now you know if the value of resistance is belongs to less than 1 ohm, if the value of resistance is belongs to the less than 1 ohm resistance, then you can say it is काय झालं आज तुम्हाला
Low resistance.
it is low value resistance. Okay, if value is belongs to less than 1 ohm, so it belongs to low value resistance, and if it goes beyond it, then we'll say it is a medium resistance, and if it goes too much beyond, that is beyond 100 kilo ohm, then we will say it is a high resistance. Now you know this in your first year of engineering, that you know this all types of scenario, value of resistance, then all this concept. Okay, so based on that, we will look for, our main aim is what? We will look for measurement of resistance. Okay, so it has been classified in three types. One is low, then medium, and then high. Now please help me, value of resistance in low, medium, and high. Yes, for low,
Less than 1 ohm.
less than
1 ohm.
1 ohm. For medium,
In between 1 to 100.
1 to आहे का
100
लक्षात?
to 1.
1 ohm to 100 kilo ohm.
100. त्यासाठी बोलत जावा, बोलल्यावर थोडस कॉन्सन्ट्रेशन वाढतं. ओके, 100 किलो ओहम. येस, व्हॉट अबाउट हाय?
So greater than 100 kilo ohm.
Than 100 किलो. ज्यांना बोलायचं त्यांनी तरी बोला, ऍटलिस्ट बाकीचे ठीक आहेत. They don't think so that it will affect, but being teacher, I know interactive session will give more aspect of learning. Yeah, so we'll start with the first method, then we'll look for the second, and then we'll look for next method, that is high. Okay, so we'll start with different methodology. Okay, different methodology. First we will look on your basic. Okay. So we'll start with we are on the measurement of resistance. We have covered measurement of low, medium, and high resistance. Now we have total 3 to 4 methods. One is Weston bridge, then we have Kelvin double bridge, then we look for ammeter voltmeter method, then Megan. Last we will have earth tester. So how many methods we will look into? We will 1, 2, 3, 4, and 5th. 5 methods are there for measurement of resistance. Okay, okay, yes. So let us start. Yes. So this is different methods for low value resistance. Okay, this is a simple method which we utilize for low value resistance. Correct. Now this is called as bridge method. First one, let us understood this what we mean by bridge. Okay, I will let you know. Okay, bridge circuit is nothing but a null method operates on principle of comparison. So right now you can only keep in mind bridge method is nothing but where we can have comparison between or we can say among registers. Okay, so there are n number of resistors, we will just compare with the help of bridge circuit. Okay, now for the bridge circuit we have classified based on the supply. Okay, so we have DC and we have AC. Correct. In AC we belongs to the inductance, we belong to the capacitance and frequency. When we come across the DC, we will have a basic passive element, that is resistance. Okay, for that we are having three methods, that is Weston, then Kelvin, and then mega ohm bridge. So apart from that, we will look into these two methods, that is Weston bridge and Kelvin bridge. Okay, for inductance we will having Maxwell, then Hayes bridge, then Owens bridge. For capacitance we will having shearing bridge, and for frequency we will having Bain bridge. For this instant you can just take screenshot if you want, because most of the MCQs we ask in such a way that for bridge experiment, for bridging the circuit, for AC supply, which methods is suitable for measuring the capacitance, or they simply give a name of that methods, like they will say Owen bridge is applicable for, so you should know it is applicable for inductance. Okay, so you can just have a screenshot or no doubt after this completion of this lecture. Yes, now the issue has been solved. So today or by the way tomorrow I will upload all the notes, all the videos that we have done through this overall session on your classroom, because there was some network connectivity issue. I was uploading all videos, but at the end it got failed. Now that issue has been solved, so today onwards you will get your all videos after the lecture immediately. Okay, so thank you for your patience. Yes, so what we are up to? Yes, we are up to the different methodology or different methods for resistance measurement. So these all methods for resistance, these are method for inductance, these method for capacitance, and this is for frequency. Okay, okay, yeah. So among these we will look for which method is more accurate for measuring resistance. We will look into it. Then we will look for what devices are used for measuring the resistance. So one device we all know, that is ohm meter. Okay, ohm meter is nothing but what? It is a one kind of instrument for measuring electrical resistance, which is expressed in ohm, because it's a ohm meter. Also, in your first year you might come across multimeter. Multimeter is also a one kind of ohm meter. If you move that particular knob, if you keep that particular knob on ohm range, so whatever the reading will acts as a ohm meter. Okay, so whatever the measurement, it is expressed in ohms, but it is also ohm meter. Okay, so this is basically multimeter, your ohm meter. These are very simplest method to measure the resistance. Okay, so what we are doing, we are either connecting that probe, either in series or in parallel. Correct. So that is nothing but a simple ohm meter or a instrument meter, or we can say your multimeter. The best one is your multimeter. Okay, so for this small value of resistance, in your first year you will come across that BB accurate bit and that particular ASCII code. Okay, so also we have come across some kind of tolerance. Okay, so if tolerance is 5%, if tolerance is 10%, can anyone tell me if a tolerance is 5%, then which color it is for 5% tolerance? Yes, for 5% tolerance, which color band is applicable? Yes, anyone? Just 1 second, guys. Okay, so let's back to our yes. Yes, please tell me. Yes, anyone? For tolerance, you might have come across tolerance. Okay, so tolerance means what? Please tell me what you mean by tolerance. And for 5% tolerance, which color band is there? Yes, you can speak. Don't drop in chat box because I have shared my screen, so I cannot visualize your chat. Yes, go ahead. Yes. For 5% tolerance, which color is there? Gold, silver, which one? Okay, fine. So 5% tolerance we have gold one, and for 10% we have silver. Apart from that, if the tolerance is 1% or 2%, we will have it. For 1% we are having brown color, and for 2% we are having red color. Okay, this is just for your information. So what these are? So these are nothing but certain indication regarding direction of first band, then second band, then third band. So there is a some small value of resistance. Okay, now we will look over into the detail of all the measurement methods for lowest one, medium one, and largest one. Okay, so we'll start with the first one, that is Weston bridge. Okay, this is first methodology for measuring low value of resistance. Okay, so as we have discussed, am I audible? At least तेवढं तरी बोला. Am I audible?
Yes, sir.
Yeah. Thank you.
Yes, sir.
Yes, thank you. So bridge method is nothing but we are just comparison. We are doing comparison among register. Okay, just keep in mind. Now let us start with the first method. This is your first method, that is Weston bridge method. So what did talk about? Weston bridge methods is nothing but a very simple method. Okay. Now first we will understand this diagram, and then we look for its working principle. So what this diagram includes? It includes AC source or DC source. Voltage is AC or DC? Please help me. Voltage is AC or DC?
DC.
How we can identify? How we can recognize this AC or DC? With the help of what happened? This is my positive terminal, this is my negative terminal, it acts as a battery, or so I'll say this is my DC. Okay, yeah. So this is one of the simplest method, and next method, the Kelvin method, is advance of this method. So first we look for the Weston, then we look for Kelvin. What they are saying, this is suitable for moderate value like from 1 ohm to 10 mega ohm. Okay, now the voltage source has been applied across some arrangement of resistance, and that is nothing but called as bridge. Okay, this is nothing but called as bridge. Arrangement of this resistance to form a particular bridge, that is nothing but bridge circuit. Here we will compare different resistance or value of that particular resistance. Okay, so this is one of the simplest and most basic bridge circuit used in measurement studies of resistance. It mainly consists of, you can visualize here, it mainly consists of how many resistance? 4 resistance. This is R1, R2, R3 and R4. Okay, here these are 4 resistance, and if you are comparing or if you are forming any Weston bridge, keep in mind there are only 4 resistance. Okay, there are only 4 resistance. Okay, now how we can find out value of resistance? What we are looking for? We are looking for different methods to calculate value of resistance. Okay, now this is one of them. This one is one of them. We are in your syllabus, we are looking for 5 methods, and out of 5, this is first one, that is Weston bridge, one of the simple methods. It is based on the bridge circuit. Bridge circuit means we are having comparison of all the resistance. We have a comparison among the resistance. So that is first one, that is Weston bridge. Okay, it consists of 4 arms of resistance. Now this is one arm. Just need use the point. This is one arm. This is another arm. Likewise, this is third and fourth. So each arm consisting of one resistance. Okay. Now among these, what is our objective? Objective is we need to find out the value of resistance. Okay, that is nothing but we are looking for measurement of that particular resistance. So for that, among these, one resistance will be unknown resistance. So here we will keep this R4 as an unknown resistance. Okay, we will keep as unknown resistance R4. So R4 is the unknown resistance under this Weston bridge, while all the remaining resistors are having some kind of value that we all know it is given in our data, and R3 is nothing but a standard resistor. Okay, why standard? You can observe here there is one arrow. So this is another standard value of resistance, or we can say variable resistance. Okay, these R1 and R2 are the normal resistance. Okay, so what apparatus we are needed? We need one unknown resistance. Obviously, that's why we are looking for this Weston bridge method. Through this Weston bridge method, we will able to find out value of unknown resistance, that is R4. Okay, and for that remaining 3 resistance will be knowing. We know the value of remaining resistance. Now they are being placed in such a way that whatever the deflection of the pointer should be 0. Means what? I'll let you know. Means what? these are two registers. Suppose if you trace the path A to B, B to C, C to D, and again D to E, means current is entering here, current is entering here. So for this point A, these are my two parallel paths. Correct? Now at point C, whatever the amount of current will flow from R1, it will flow from R3 and it will comes here. Whatever the amount of current I2 and I4, it comes here, and cumulative current will again get back to the pavilion, that is to the source side. Means what? Means what? A bridge circuit always works on the principle of null deflection. Now then, what you mean by null deflection? Now you have introduced another new word, that is null deflection. Null deflection means what? That is, we vary some turn parameter until this detector will show zero reading. The detector means this one. So at the center you can observe some detector. This is not ammeter and voltmeter. Please keep in mind. This is only detector. So that is nothing but galvanometer. Okay. So we will vary a parameter until this detector show zero value. Okay. Now here we will use mathematical relation to find out the unknown value in terms of varying parameter and other constant. म्हणजे काय? सर म्हणजे काय? म्हणजे we want to obtain, so we have certain relation. So in the checkbox you can observe here, R4 is the unknown value of resistance, and we are having remaining R1, R2 and R3 are known resistance. So we will form certain pair. So with the help of that pair, we will vary value of that particular resistance, and when this pointer, the central pointer, that is galvanometer, will show null deflection or will show zero deflection, then we will say now bridge is my balance bridge, and at that time whatever the value we will obtain, that is nothing but value of that measuring resistance. Okay. आता हे कसं, how it will work out, we will look over it. Okay. Suppose so we were having this. What is the balance condition? First we will I'll let you know what we mean by balance condition. What they are saying balance condition is no potential difference across the galvanometer. So there is no current through galvanometer. जर या galvanometer मधून currentच flow झाला नाही, means what? Means what? All the resistors are having now a equal amount of current, because you know KCL and KVL. Current law काय सांगतो KCL चा? Amount of current inside and amount of current flowing outside is nothing but summation is nothing but zero. Okay. So if there is no current, that's why a galvanometer will not have any deflection. Basic example. If you switch on particular appliances, if you switch on your TV, okay, if you switch on your TV and after some duration of time you switch it off, correct? Have you observed any certain amount of current is flowing through that particular appliances? No. Why? Because each appliances are carried out one phase and one neutral. So whatever the amount of current flowing through that appliances will again return back. This is nothing but hence and forth cycle is goes on repeating this cycle. We are working in our domestic, we are working on the AC supplies. Okay, so it goes on continuous one. Live path is there, return path is there. So there is a complete circuitry. Okay, if there is no return path, then there is a chances of short leakage current, and that's why we'll observe the person who is operating that appliances will observe shock, correct, electric shock. So that's why phase is there and neutral, that is return path is there. Same happen, instead of appliances we are keeping our bridge over here. So what the role of bridge? We will vary certain value of resistance, and at one point we will come to know, yes, now my pointer is at zero position or it is not going for any kind of deflection. It means my bridge is now balanced. Okay, so at the start I told you that in bridge circuit all the methods are operate on null method and principle of comparison. So we will just compare the value of each resistor and we will look into the value of unknown resistance. Okay, we will look into the value of unknown resistance. Okay, now I'll just clear it out, and again we will look into. Yes, now please let me know value or basic formula of Ohm's law. Basic formula. Make it fast. Then we will have lunch break. Yes, basic formula of Ohm's law. कोण सांगतंय? Yes, make it fast. Basic formula Ohm's law. V is equal to. बोला रे पटपट. आज काय रेग्युलर मेंबर नाही आहेत का?
IR.
E is equal to IR. Okay. Now you have to apply this formula for a branch. Okay. Suppose current is flowing from this one. Now current has been entered at point A, and it being a parallel connection, it is get divided. Okay. So please help me for voltage across VAD branch. VAD branch. VAD means this branch. Okay. So for this branch, we are having only one element, that is R1. Can anyone please help me for finding the voltage drop across ED branch? Yes, please. You know the basic formula, V is equal to IR. Now just you have to think on it and just let me know what is the voltage drop across branch ED. Which V is equal to IR. So here I is nothing but I1, correct? And resistance is nothing but what?
R1.
R1. कळलं का तुम्हाला आता? So what will the voltage drop across the branch VAD? That is nothing but current, amount of current I1 flowing through the value of resistance R1. That is V is equal to I1 R1. Okay? Yes. Now please help me for VAB. Now you should be very fast in this. VAB, please make it fast.
I2.
Yes, I2 R2. What you are simply doing? You are simply applying again Ohm's law. That is V2 is equal to I2 R2. Clear? Yes. Okay. Now, someone please help me for VCD or VDC. Yes, please. VDC.
I3R3.
Very good. I3R3. Yes. पुढचं सांगा कोणीतरी पटपट. VBC. Yes, VBC.
I4.
I4 and R4. Okay. So among these, which one is unknown? R4 is unknown. That value we need to find out. Correct? Yes. Now we know our, again we will go back to our basic formula of series 1 and parallel 1. We know the value of series 1 and parallel 1. In series, voltage, in series current is constant, and in parallel voltage is constant. Okay, suppose I am saying at point A, voltage drop across the branch VAD and voltage drop across the branch VDB is nothing but equal. Okay, clear? Also, now voltage drop across the branch VDC and voltage drop across the branch VBC is again equal because they are in parallel. Now we know value of VAD, that is nothing but I1 R1. So here I1 R1, then same way I2 R2, I3 R3 and I4 R4. Okay. Now let us just concentrate here. I1, I2, I3, R4 are current in resistance correct? Now you know I1 हा जो A to B ब्रांच मध्ये फ्लो होणारा करंट आहे, सेम करंट इज फ्लोइंग थ्रू which branch? I1 is entering here, same current is flowing through R3 branch. Is it clear? I2 flow current is there, which is flowing through AB branch, same current is flowing through R4 branch. So we will derive one equation that I1 is equal to I3 and I2 is equal to I4. म्हणजे amount of current flowing through I2 is same in amount of current flowing through I4, because I2 and R4 are in series. I1, R1 and R3 also are in series. So we will write equation for I1 and I3 and I2 and I4. Okay. So if you rearrange this, we'll come to know, what will come to know? R1 by R3 is equal to R2 by R4. आता हे कसं आलं? Okay, so for that we have to rearrange the term of, we have to put the value of I1 and I3 and I2 and I4. So you will get a mathematical model of R1 divided by R3, R2 divided by R4. Now I have not included that mathematical model in your curriculum. Why? Because it is not needed. It's just a one-step calculation. So if you just compare or just equal all the values of current, you will come to know within one single step, you will come to know the value of R1 and R2, R3 and R4. Okay. So now what is our aim? Our aim is to find out R4. Okay. Now just we will, if you simplify this, we will get the value of R4. So that is nothing but R3 will come at RHS side, R2 by R1 into R3. So finally we will get the value of R4 as R3 into R2 by R1. Okay, but here they are saying R4 is unknown. Okay, R4 is unknown. That's why we have modified it. But for your convenience, you can keep only this in mind. That is R1 divided by R3 is equal to R2 divided by R4. Okay? This you have to keep in mind. Okay, that's why here I have written as OR, because here we are find out unknown resistance R4. In some cases they might say R2 is unknown resistance. So you have to just rearrange for R2. Okay, so for R2, how equation will come? R1 divided by R3, just this R4 will get multiplied this. Okay, so this is nothing but a simple method of Whetstone bridge. So what does it talk about? So Whetstone bridge is nothing but a simple bridge formation where we compare the value of all resistors on the basis of Ohm's law. So basically, in previous also we have said it is a bridge circuit. We will just work on or operate on the principle of comparison. So here we just compare different methodologies on the basis of certain basic laws. So here we have used Ohm's law, then we have used some series and parallel combination of current, and what is the amount of current in parallel combination, what is the amount of current in series and parallel combination. And in that particular respect, we just equal all the conditions, and finally we will write for the equation R4 is equal to R3 to R2 by R1. Now this is exceptional. Okay, we have to most concentrate on this one. That is R1 divided by R3 is equal to R2 divided by R4. Clear? Okay. Now among this R3, you will find out something different. There is one arrow. So this is belongs to the standard value of R. Standard value of resistance. Okay, so that's why it is known as standard arm. Okay, arm ka, because within this branch there is only resistance. So we'll say this is a standard resistance, and in which branch it is belong, that is standard branch, or we can say standard arm. Okay, and the rest of the two, that is this at the introductory part, we are having R1 and R2. Okay, so this R1 and R2 are known as ratio branch or ratio arm. Clear? So 3 to 4 MCQ will form here that ratio arm or ratio arm resistors are located at the entrance side, and these are denoted as R1 and R2. Mostly R4 is the one where for which we are going to find out the value of particular resistance. That is nothing but R4. This is nothing but for which we are going to measure our particular value. Okay, and it belongs for what range? It belongs for range of 1 ohm to 10 mega ohm. Okay, which parameter is there? That is nothing but galvanometer, which works on the no deflection or zero deflection. Zero deflection part, the galvanometer work when it shows zero deflection. We will say our bridge is balance, and at that time whatever the value of, we will use this mathematical equation, and the value we will obtain, it is called as that particular value of unknown resistance. And this is a simple working methodology of Wheatstone bridge. Understood? Okay. Yes, so we are on unit number 2, and we are looking for section B, which is nothing but your measurement of inductance, okay, as well as your capacitance. So I'll say this is capacitance as well. So already we have discussed the basic difference between AC and DC bridges. Also, we have cumulative described different detectors, what are the different sources, how resistance will be present in terms of AC bridges. So all this prerequisite part we have already covered. Now, as per your curriculum, we are having Maxwell bridge, Maxwell inductance bridge, and then Anderson bridge in your AC bridges. Okay, so let us see all these three bridges one by one. Before that, this is the one slide. We will explain the slight difference between AC as well as DC. Okay, as so far we have covered the difference between AC and DC, but still, by looking into the picture on your screen, can anyone tell me what is the difference between AC and DC? Yes.
तर DC मध्ये रेजिस्टन्स आहे आणि AC मध्ये इंडक्टन्स.
So, this is one difference. Hello. अजून मी लेक्चर घेऊ आधा घंटे. Yeah. Second one is resistance and this impedance. What about second difference? Any other difference in terms of source? Here it is AC and it is DC. Then in terms of detector, okay, other procedure, other circuitry, other connection diagram will remain same. Other equation also remains same. Here we have derived the equation R1 into R3 is equal to R2 divided by R4. Sorry, R2 into R4, and we have seen its modified version also. R1 divided by R2 is equal to R4 divided by R3. In same way, only resistance now will replace by inductance. Clear? So this is the basic difference between AC and DC bridges. Now we will start with our first method, that is Maxwell bridge. Okay, and in that Maxwell bridge, so I will first elaborate Maxwell bridge. That's why most of the students get confused. Sir, the Maxwell bridge, Maxwell inductance bridge, and then capacitance bridge, these are different? No. Both these inductance and capacitance are derived from this Maxwell bridge. Okay, so I have put out all this picture in one slide itself. So let us see what is mean by Maxwell bridge first. So Maxwell bridge is the nothing which is used.
Sir, the screen is not visible.
Is it? Just one second. Now,
Yes, sir, visible.
so from where it stops? From starting or just? Okay. So this part we have already covered. हे बघितलं होतं का तुम्ही का हे सुद्धा ऑफ होतं?
बघितलं.
This one?
No, sir.
Okay. So this part we have covered. Okay. First again start with सांगत जा रे असं. Okay. So what I'm telling, Maxwell are classified as Maxwell bridge for inductance and Maxwell bridge for capacitance. Okay. So what do you mean by first Maxwell bridge? I think in last visit we have covered this about this Maxwell bridge. So any circuit, what it tells, any circuit which is used to calculate unknown resistance, unknown capacitance, unknown inductance, frequency, any mutual inductance, so which will operate on AC bridges, AC source, that will comes under the category of AC bridge. And when we are referring this bridge on the principle of inductance, so we will call it as Maxwell bridge. Okay, so Maxwell is the one scientist who developed this method, who developed this process, and what was its perception? These bridges will work on the principle of balance ratio of impedance. So here what we include, instead of only resistance, we include here impedance. Okay, so because of this impedance, we will obtain null deflection. So all these Z1, Z2, Z3, Z4, these are the impedance, and as we know, these are again we are calling as ratio arm. So because of this ratio arm, by varying certain parameter, we will get a null deflection, and through this we can proceed for our accurate result. This is what the aim of any bridges. Okay, and from this we will derive our balance equation from the circuit to determine unknown, whether it is resistance, whether it is capacitance, and whether it is inductance. Okay, so these AC bridges are used where we are using these AC bridges for communication between different systems. Then for network, so this network is nothing but our electrical network, or we can say electronic network, where complexity is much more. Okay, so these bridges are being used in electronic devices, communication system. So what is its use? Because of this Maxwell bridge, because of this Maxwell inductance bridge, because of this Maxwell inductance capacitance bridge, most of the application will get its actual value, or we can say accurate value, throughout these particular bridges. So that's why we are looking for this Maxwell bridge. Okay, so Maxwell bridge, if you Google, you will find out as Maxwell Wien bridge or modified Wheatstone bridge, or you can find out inductance capacitance bridge. So all are nothing but same. Okay, in your curriculum they have mentioned as Maxwell bridge. So that's why I have highlighted here Maxwell bridge. But if you just go on the global search, you can find out many words for the same bridge, because Maxwell is one method through which we can have certain permutation combination. Means with the help of Maxwell bridge, I will have inductance. With the help of Maxwell bridge, I have capacitance. I will have combination of these both, and resistance is always present here. So through this, we can say this is Maxwell Vein bridge, we can say this is a modified version of Wheatstone bridge, or we can say it's a Maxwell inductance capacitance bridge. Whatever the name you want to do, you can. Okay, so these are some things about the Maxwell bridge. Okay, now let us start with our first one. How we can use this for null method. Okay, so that is the most important thing. Okay, here we are using certain detector. So if you consider in DC, you can observe here it was a galvanometer, and in AC it's a detector. Please keep in mind, most of the MCQ get confused between the galvanometer and indicator. Function is same. Whether you go for AC bridge or whether you go for DC bridge, function is same, functionality is same, checking points are same, objective are same, both are giving null deflection, only the change in source and your element. That's the important rule. Okay, yeah. So as we have covered this part also, means your equations are also same, only the change in your parameter. So based on that, we are having certain types of methodology for Maxwell inductance bridge and Maxwell inductance capacitance bridge. Okay. So before they going to this, we will first look for the for which purpose we are using it. Yes. So bridge circuit is used for measurement of medium inductance and can be arranged with the result of considerable precision. So precision is the one which is the characteristics of your measuring instrument. Okay. Here we are going to use two arm that are nothing but is ratio arm. Here we are going to use resistance. Here we are going to use some balance relation among these, and depending on these we will get our deflection of the pointer. Okay, so first let us understood what these AC bridge are consisting of. Okay, so this is first what we are looking for, Maxwell inductance bridge. Okay, so there are two types of bridges. There are two types of these Maxwell bridges. One is inductance and another one is capacitance. Okay, so let us see these different types one by one. So this type of bridges, where with the diagram is here. So this type of bridges is used to measure unknown inductance value. These type of bridges are used to measure unknown inductance value. So you can observe here, along with the inductance, they are having resistance. Okay, so it is a combination of resistance and inductance. Okay, that's why we have called it as impedance. Okay, yeah. So the aim is what? To measure the unknown inductance by comparing it with some standard value of self-inductance. Okay, so two arms of your bridge, Now I think you are now well familiar with this arm, the bridge, and the null deflection point, these kind of keywords. Okay, I hope so that you are all are aware about this. Okay, so this type of bridge used to measure unknown inductance. This part we have covered. Now what we are actually doing, we are simply comparing. We are simply comparing your unknown value to be measured with your standard value. Means one will be the known and one will be the unknown. We are just comparing, and if these two arm of the bridge circuit it get balance, when it get balance, when it will show null deflection, and whatever the amount of that particular inductance is nothing but your unknown inductance. So means what? Simply we are comparing the ratio arm. So these are the ratio arm, and through which we are balancing our detector value. And if it is so the D0, that is a null deflection, we are saying it's a balance bridge. Means what? Means what? In this case, the AC voltage source we have supplied, correct? And null deflectors are connected across this particular junction. So suppose B and D are the two junctions in which we are connected null deflector, and A and C are the points where we have connected our AC source, correct? So what do you mean by first balance condition? Okay, so balance condition So instead of directly going to the formula, let us first let me clear what is this L1 and L. So L1 will go one by one. L1 is nothing but unknown inductance. L1, this is my unknown inductance. Okay. So along with N1, we have resistance R1. So this is R1. L4 is what? Variable resistance. L4. Where is L4? This one is L4. This is L4 along with its fixed resistance R4. Okay. Now this R4, now this total branch is of variable inductance. Okay. So R4 is nothing but what? Variable resistance connected in series with L4. This is what we have covered in our prerequisite. Okay. Now this R2 and this R3 are fixed value of resistance. Clear? Yes. Now, when we are saying this balance equation means what? This R2 and R3 are nothing but your non-inductive resistance. R4 and R1 are the inductive resistance because they are connected in accordance with the inductance value. And when we are supplying AC power, there is, because of the inductance and resistance phenomena, your bridge will not get balanced. Through this, now we know the procedure. We have done one experimental also on basis of Kelvin double bridge. What we are doing? We are just simply checking, switching on the particular AC supply. We will check for all the precondition, and accordingly we will just vary certain types of input, and we will get null deflection at this particular detector. Okay, so that we will say this is my balance condition. Okay, so same procedure here we will follow, only here instead of resistance is already there, we have just added inductance. Okay, so this is known as Maxwell inductance bridge. Okay, and at the balance conditions, this is what we are talking about at balance. So at balance, what we are saying, R1 plus j omega L. Now this is nothing but your Z1, correct? Into R3. R3 is nothing but what? Which one? This is, because this is a cross arm product. If you just remember this one, yes. What they are saying, what we have seen in DC bridges, R1 into R3 is equal to R2 into R4. Here in AC bridges, Z1 into Z3 is equal to Z2 into Z4. Same logic will apply here, but if you remember, here Z3 is what? Z3 is what? Is equal to only R3, because inductance term is not present here, correct? So further term gets cancelled, so Z3 is equal to R3. Here also Z2 is equal to R2. Z1 is equal to what? R plus JXL. Z4 is equal to what? R4 plus JXL. Correct? So this becomes Z1, this becomes Z3 is equal to Z4 into Z2. This is what we have look for AC bridges. Z1 into Z3 is equal to Z2 into Z4. Correct? Z1 into Z3 is equal to Z4 into Z2. And from that, this is our balance condition. Now from this balance condition, we can derive any equation. So this is equation which we have derived for inductance and capacitance. Now why we have derived it for L1 and R1? Because in this bridge, we have considered Z1 is my unknown impedance. Correct? How? Because at the start we have defined L1 is my unknown inductance along with R1 is my unknown resistance. So Z is equal to what? R1 plus JXL. So XL1. Correct? So it becomes, obviously it becomes Z1. Correct? So that's why it is L1 and R1. So we can note down this. L1 is equal to L4 upon R2. L1 is equal to L4 into R2 upon R3, and R1 is equal to R4 into R2 divided by R3. These are the equation for Maxwell inductance bridge. Okay. Now this is one example is there, but before that I want to cover next method, and after this we will go to that go back to that particular example, because the difference what we are looking for that we need to consider. So this is next method of Maxwell. First one was OT inductance. Here we have considered inductance plus along with capacitance. Okay, so here what we have considered? Here we are considering inductance along with capacitance, and that's why it is named as Maxwell's inductance capacitance bridge. Okay, what? Maxwell's inductance capacitance bridge, or we simply call as LC bridge. What? LC bridge. Okay, yeah. So this type of bridge is used to measure again unknown inductance. How? By comparing it with standard value or standard capacitor. Why? Because here we have included a capacitor instead of inductance. Now which type of inductance we have replaced, we will see. Okay, so this is another method, Maxwell inductance capacitance bridge, used to measure unknown inductance value by comparing it with a variable standard capacitor. Okay, again your source will be AC voltage source, and for our deflection we are using again null detector, which is connected at junction. So I will show a junction here. So in this bridge, inductance is measured by comparison with the variable capacitance. The connection you will see here, one of the ratio arm has resistance and capacitance in parallel. So this is the point. Yeah. So what was the difference? What is the difference? If you just compare these two, what is the difference? Instead of here, what was there? One inductance along with resistance and one inductance along with resistance are variable. So instead of inductance, what we have done? We have just cancel out that variable inductance, and here we have put out variable capacitance along with resistance. So obviously, what we are looking for, we are going to find out unknown inductance. So this will be my unknown inductance. That's what I need to find out. Correct? Correct. So let's again see this. L3. L3 is what? Yes, it is unknown inductance. Where it is? This is L3. C. C is a variable standard capacitor. That is this one. R1, R2, R4 are pure resistances. So this is R1, R2, and R3. These are pure resistances. R3 is effective resistance of inductance L3. So now again we will say at balance condition. Balance condition means what? Means what? At this cross arm, when this pointer will get deflected at which position? At balance condition, your pointer this detector will give null deflection. It will not give any kind of deflection. Okay, please listen very carefully. At balance condition, it is not showing any kind of deflection. That's why it is called. We say that it is the balance condition. Okay, and to achieve that balance condition, we are just simply comparing your unknown with your variable capacitance. In Maxwell inductance bridge, it was only inductance. Here we have just make a modification, and what we have obtained, instead of inductance we are replace it by capacitance. Okay, so finally we will obtain this kind of relation. Now this derivation part is now not doesn't matter in your curriculum, because most nowadays it is concentrating on some conceptual part. Okay, because derivation is again one page lengthy procedure, and at the end what we are getting is final term. In theoretical exam it is of course it matters, but it is MCQ online exam, conceptual is matter. Okay, so this what we are obtained at in same procedure, same methodology. Only the point to be noted here, we are replacing variable inductance by variable resistance. This is the point for inductance capacitance bridge. And who explained this? It is explained by Maxwell double bridge. Okay. Now we go back to the particular example. What they have given, this is problem on Maxwell bridge. Okay, as at the start I have declared that most of the time we have in our curriculum we have given Maxwell bridge. Okay, but Maxwell bridge are the classified into two categories. First one is inductance and inductance capacitance. Correct. So let us start with the example. What they are saying: determine the value of unknown inductance required to balance the bridge. Okay, means what? Your bridge will get balanced when it will show null deflection. Definitely it will show null deflection. And to achieve that bridge, I need to vary my inductance. Okay, and that value we are going to find out. Right? This is the agenda. Okay. If the four arms of the Maxwell bridge are arranged as follows: arm AB is non-reactive resistance, which is 1 kilo ohm, in parallel with the capacitance 0.5 microfarad. Okay, suppose I'll say this is resistance, and along with it, if I say it is a capacitance, just we have seen this diagram. Also, now BC is another branch of resistance 700 ohm, and CD is unknown inductance. So this is, I'll say this is unknown inductance, and RBA is non-reactive. Suppose this is 700 and this one is 600. So what we will get? So at the end, what we are going to find out? At the end, what is our aim? Here it is. Yes, this was the. I'll rub it again. Yeah. So capacitance is given, resistance are given, inductance is given. Along with these are the resistances given. Now what? Sorry, inductance that we need to find out. Resistance values are given. Correct? And capacitance are given. So what is the formula? L is equal to C into your non-inductive resistances. Okay? Yes. L is equal to C into your non-inductive resistances. I am again telling you, don't be stuck at this R3, R4 and C4. Just be a conceptual one. Because if I am representing, these are just only notation. I am representing this resistance. Okay? If I am representing here by R2, in another case, if you go on the crossing checking book, you can observe here R3. So don't get confused. Okay, we have learned here R2 and this is R4. No, these are only notation. Okay, only check. In some case, it might happen this branch will appear at this level. Correct? This might happen. What you have to check for? You have to check for the balance condition. Whether we are achieving balance condition, yes, then go on. Correct? Yes. Okay. So what is the equation? L is equal to capacitance into that particular non-inductive resistance. Okay. So this is what is present over here. Okay. So we'll simply put the value of R2. So what is value of R2? It's 600 ohm. Then 700, and capacitance they I think already they have given. Where it is? Where it is? Capacitance value, yeah, here. 0.5 microfarad. So 0.5 into 10 raised to minus 6. So we will get the value of inductor. So such example they might ask in your exam. Only you need to know all these final equations. Here is the equation तुम्हाला माहिती असेल, then you are able to solve any equation. Yes, but they will confuse you. How? They will write here to calculate value of R4. So R4 is equal to like this. So the thing is, you have to just capable to arrange all these things. तुम्हाला इक्वेशन चेंज करण्याची ability तुमच्यामध्ये असेल, it will only occur when you have understood this conceptual method. Means what? They might ask for R4. Okay. Then most of the students get confused. Okay, R4 equation they have not given. I have only studied for L3, R3 and this question parameter. But you have to just arrange this one. If you get able to arrange this one, then definitely you will able to solve any MCQs. Okay, because most of the time MCQs are very simple. Only they are your thinking based ability. Okay, they are only checking for thinking based ability of your conceptual theories. Okay, because now you are not appearing for the theoretical exam. Yes, in theoretical exam they might look for your all MCQ. They are just for have practical approach how we can going to vary. Likewise, in double bridge, what we have done, we have looked for a digital experimental setup. The lower arrow, we are just changing the input. This is an experimental setup. Here, what we are doing, these are the variable variables. Because it's a part of EC. When we are dealing with the frequency, it is a part of EC bridges, and Maxwell is the methodology where we obtain the balance condition. And the advantage of this balance condition is what? We are obtaining a bridge circuit which is independent of frequency. Okay, so because of this, it is used to measure different range of inductance in electronic devices like your audio frequency, your power frequency devices. Okay, so because of these high ranges, we just simply comparing our standard one with the variable inductance. Okay, so these are the application of Maxwell bridge, and that's why we are move ahead for this Maxwell bridge. Okay, so what are the application of Maxwell bridge? One is communication system, then electronic devices, then your power audio frequencies. Correct. So these are some certain types of example. These are certain types of example where we are using such Maxwell bridge. Okay. Yes. Now I have a question for you, and then we will look for, yes, still we have 20 minutes. There only one method is remaining. So first we'll look for this one, and then we'll have some question and answer for this all the bridges. Okay. So this is another methodology. Am I audible? Modification.
Yes, sir.
We are modifying something means what? We are overlooking or overcoming some drawback of previous method. Correct? This is nothing but modification. So which method we have just looked for? We have just completed a method of Maxwell inductance and capacitance bridge. Okay, and we are simply modifying that particular bridge, and we have named it as Anderson bridge. Okay, means what? There are certain loopholes in Maxwell bridge, and which is identified by Anderson. Correct? And with that base, he proposed some methodology with some kind of modification that is known as Anderson bridge, not Anderson double bridge. So what we are use for, again we are using it for measurement of, he added one standard word, that is self-inductance. So he is saying my methods is used to measure the self-inductance of my particular circuit. Okay, so let us see how. Okay, what he have changed? Okay, if you remember, the basic difference between Anderson and this Maxwell inductance is what? Okay, what it was? Capacitance was in parallel. Okay, I have already highlighted this one, parallel. Okay, and if you just look into these, now it is in series. This was just a modification of Anderson, and remaining methodology, remaining procedure is all remain same. Only he thinks that if I just change the position of this capacitor from series to parallel to series, I'm able to get a self inductance from that particular circuit. Okay, and that's why Anderson come forward with some certain kind of modification, and he proposed one method that is called as Anderson bridge. Remaining things are same. Your AC source is same, your bridges is same, your detectors are same, even your inductance and resistance position are also same. Only they have added the capacitance, and that's why a small amount of resistance get added. That's it. Okay, so this is what Anderson bridge. Okay, now What's the purpose? So the purpose is what? He's thinking a large number of AC bridges, if there are large numbers of AC bridges are available. So with the help of Anderson bridge, if I use this to measure the self-inductance of that particular coil, so it will be helpful for the measurement of capacitance and resistance, which is used for the balancing this particular circuit. Okay, means what? If you just think over it, now your Z is not only L plus R, here it becomes R plus L and plus C. Okay, so you have included all your passive element, and that's why your Z get modified. So in equation also you can identify the complexity of this. Yes, correct. Okay, now this is not actually necessary to just go for it. You just only keep this in mind. Okay, the value of resistance is again same, R1 into R3 is equal to R2 into R4. See, I'm again telling you all the equation are remain same, only the modification part is taking place.
Yes, so I think this is for enough for today's session. We have discussed with the measurement of inductance, resistance, and capacitance. In afternoon session, we'll continue further. So I'll stop my recording now.